review our activation circuit of our microcontroller before we move on today. So this is our original pin diagram of 8051. We have our port 1 here. This is my reset circuit. We have our port 3 available here. These two are the crystal lines. This is my ground pin. This is my port 2, complete 8 pins. This is the external access pin. And we have port 0 here. And finally, the power supply pin. So let us quickly revise our activation circuit, or how to activate this particular microcontroller, which I have already given to you, but then this is a quick revision of that. So the first point is, how do we activate a embedded microcontroller? This is the embedded microcontroller what we are using in our part 1 of our curriculum, which is an Atmel microcontroller, which is 8089C51 microcontroller from Atmel. So you already know what is the difference between activating a normal digital IC and a microcontroller like 8089C51. A normal digital IC essentially has only 2 pins, like the power supply pin. If you say 7400 quad NAND gate, this fellow has 14th pin as power supply. So if you give power plus 5 volt here and connect pin number 7 to ground, so these two connections are good enough for making this IC operational, which means if you supply inputs at points 1 and 2, you will get the output at point 3. So this is a pretty straightforward IC. So the moment you connect the power supply pins to power supply and ground, the IC is immediately operational. But unfortunately, that is not the true case for a microcontroller. A microcontroller is a complex digital machine which requires certain additional things to be taken care of in order to make it functional electrically as well as logically. So that is the first discussion that we are going to have today. How am I going to activate a particular microcontroller, more specifically Atmel 8089C51 microcontroller? So as you are already aware, there are 5 important steps that we have to take into consideration before you activate a microcontroller. First one is the power circuit, which supplies the necessary DC power to the microcontroller. Second one is the oscillator part, which supplies the clock pulses for the operation. Third one is the reset circuit, which will initialize the microcontroller and it will bring the microcontroller to a known state before it starts executing the user program. And finally, the firmware locator pin, which will tell the microcontroller from where it has to fetch the source code from, whether it has to fetch the source code from internal ROM or whether it has to fetch the source code from external ROM. And finally, the last part, namely the firmware part, which will add intelligence to the microcontroller and it will tell the microcontroller what exact function it has to do. So the first 4 requirements, 1, 2, 3, and 4, are electrical requirements. And the last one is the logical requirement. Logical means which will essentially add intelligence to the microcontroller. So we'll quickly revise them one by one. Before we move further, I wanted to understand whether all of you are able to hear my voice once again. Please confirm and tell me whether you are able to hear my voice once again. Okay, thank you. Okay, good. Now let us proceed further. We will quickly go through all these concepts one by one and try and understand how things work. uh, the first one is, of course, the power circuit part. Uh, yes. So this is my power circuit. The objective of having the power circuit is to derive uh, plus 5 volt and ground. Uh, yes, Siva, you have something to say? Now, if you have any doubt, you please have it and write it in your notebook, and we will discuss at the end of the session. Since this is an online session, I cannot directly address each one of you. Uh, if you have any queries or doubts, you please reserve them at the end of the session. We will address them one by one. I will unmute you individually once you raise your hand, so you can take up the question at the end of the session. So if you have any questions or queries, you please note it at the notebook, and then we'll have a discussion at the end of the class. Thank you. Coming back to our discussion, uh, the power pins that are concerned with our microcontroller are pin number 40 and pin number 20 respectively. Pin number 40 is my power supply pin, where I apply plus 5 volt. Pin number 20 is my ground pin, where I connect 0 volt or ground. So these are the two pins that are concerned with power, as you must be already aware of. So the next thing is, we need to design a small power circuit. You may ask a question, why don't we take this power directly from our regulated power supplies and connect directly plus 5 volt and ground to the microcontroller? Why should we design a power circuit? Well, you can connect directly the plus 5 volt and ground from the regulated power supply in lab uh, for learning something. But when you are designing a product where this microcontroller is going to be part of it, obviously you need to design an independent power circuit which supplies the necessary power for this particular microcontroller. You cannot obviously ship that particular product along with regulated power supply. So it is always necessary that you design a small power circuit which not only powers the microcontroller but also powers the other accessory circuits. So this is not a rocket science here. So we take a 230 volt AC and we have a small bridge rectifier here. You can either construct the first of all, this input 230 volt is scaled down to 12 volt AC by a step down transformer. This is the transformer. In the next stage of the transformer, you have your rectifier stage. You can construct this rectifier by using 4 discrete diodes, or you can go for a rectifier package like this. These bridge rectifier packages are available these days with the 4 diodes built inside, which will save a lot of space in your printed circuit board when you are fabricating this as a PCB. So people these days are not preferring discrete diodes for building bridge rectifiers. Rather, they go for built-in rectifier packages like this. So which is what is shown here. Followed by the rectifier. The rectifier output would give you a full wave rectified output like this. And at the output of the rectifier, you have a filter circuit. The most predominantly used filter circuit is your shunt capacitor filter. We use a 1000 microfarad shunt capacitor filter. Followed by the filter capacitor, you have the regulator circuits. We have 2 voltage regulators connected in cascade. The first one is a 7812 voltage regulator, which has 3 terminals: input terminal, output terminal, and the ground terminal. This fellow takes an unregulated 12 volt at the input, and it will give you a regulated constant 12 volt output, 12 volt DC at the output. So at the end of 7812, you will get a 12 volt DC here. Followed by 7812, you have 7805 voltage regulator. 78 voltage 5 regulator gives you, again, this has three terminals: an input terminal, an output terminal, and a ground terminal. 7805 gives you plus 5 volt at the output. Now, this is your practical representation of 7812 and 7805. And in order to know whether the power is available in your board, it is always better if you connect a power LED to the circuit, current limited by a resistor here. So if the power circuit is working normal, and if the circuit delivers constant 5 volt at the output, this power LED will illuminate and tell you that there is a power in your board. So that is a quick and easy way of identifying whether a particular electronic board is powered or not. So it is always customary to end your power circuit with a power indication LED, current limited by a resistor, which is what we have done here also. So there is nothing special here. This circuit you would have learned many number of times in your basic classes. The entire power chain consists of a step down transformer, followed by a bridge rectifier, followed by a shunt capacitor filter, followed by a 7812 voltage regulator, which gives you plus 12 volt DC, followed by 7805 voltage regulator, which will give you plus 5 volt DC. This 5 volt DC is what we use for powering our microcontroller. So we connect that one to pin number 40, and the ground of this is shorted to the ground of my microcontroller. This concludes my power circuit. I hope you are following what I'm discussing here. As far as the power circuit is concerned, there is nothing special. Like we have only two pins which are concerned with the power. So pin number 40 is connected with plus 5 volt, and pin number 20 is connected to ground, which is 0 volt. So this is pretty straightforward. What do you mean by power issues or power problems when you design a power circuit? Again, this concept we have already discussed. When you are designing a power circuit, most likely you will encounter this kind of these two kinds of power issues. One is a glitch, the other one is a brownout. So when you design a power circuit, when you draw a graph between time on the x-axis and voltage on the y-axis, the ideal expectation is you should get a constant 5 volt DC like this. Even if it is not a perfect straight line, you will have small minor ripples like this. So this is your ideal expectation, plus 5 volt DC. But when you are designing practical power circuits, there are chances that you may end up in getting power problems like a glitch or a brownout. What is a glitch essentially is a very sharp dip in power supply voltage from 5 volt to 0 volt for an extremely small time, and the power and the voltage rises back to 5 volt, which means this glitch essentially happens for a very small duration. If you see what is the time duration of this delta T lasts only for a few microseconds, not more than that. So it is an extremely short phenomena where the power supply voltage dips from 5 volt to 0 volt for an extremely short period of time. It is an extremely short period spike where the voltage is pulled down to 0 and then it returns back. This is called a glitch. The other potential problem that you may encounter in a power circuit design is a brownout. A brownout is a slow sag of voltage. This is a brownout condition. This is called a slow sag. Unlike a glitch, it is not a very sharp dip in voltage, but it is a very slow sag of voltage. From 5 volt, it drops to 4, 3.5, and then the voltage settles down to 5 volt like this. So these are the two potential problems that may arise when you are designing a power circuit, a glitch and a brownout. Of the two, which one of the two is potentially more dangerous if you ask? a glitch or a brownout, this fellow is potentially more dangerous. This is more dangerous than a glitch. The reason is straightforward. If glitch happens, all that happens to the microcontroller is it is temporarily disconnected from plus 5 volt and the power regains back to 5 volt. That means it is momentarily off for a very short span of time. So when it is off for a short span of time and it is turned on again, the microcontroller resets itself and then it starts its operation once again when the glitch happens. If a brownout happens on the other hand, like when the voltage slowly drops to 4 or 3.5 and then it regains, most likely the microcontroller will not begin its operation once again. The microcontroller stops performing, stops working when brownout happens. So you have to be more careful in dealing this brownout than this glitch. That is why we normally use brownout detection circuits. These brownout detection circuits are used to detect whether the power supply line is experiencing a brownout or not. In the event of a very small drop in voltage, probably the microcontroller will take the help of a brownout detection circuit to regain its operation once again. So what this brownout detection circuit essentially does is it has 3 terminals once again. One is input terminal which has to monitor. One is called the threshold voltage that you set, which you normally set by using a potentiometer. And the output terminal of this you connect to reset pin of your microcontroller. Say for example, the input voltage is 5 volt and I am setting the threshold voltage at plus 4.75 or something like this. This brownout detection or BOD normally keep quiet as long as the input voltage goes below 4.75. When the input voltage goes below 4.75, this fellow triggers the reset of the microcontroller where the microcontroller reset itself. So this kind of brownout detection circuits you normally use only when you are going for extra precautionary measures where such a small stoppage times of the microcontroller is not permissible at all in all safety critical systems. A normal system like where you are dealing with simple applications where this kind of power issues are acceptable, then we no longer use brownout detection circuits. This is just for your understanding. Keep a note of this. So at this point in time, I just wanted to know your inputs, whether you are with me or not. So you can just ping your chat box and tell me whether you are following what is going on in the class or you are following what is going on in the class. Okay. Okay, thank you. So we'll proceed further. So that's all regarding the power. The next one, what we are going to discuss is the reset circuit. The reset, I'll just the reset of this particular microcontroller is pin number 9. This is my reset pin. You know what is the definition of a reset, right? So what is a reset? Reset is a manufacturer defined subroutine which will initialize the processor and bring the processor to a known state from where it begins executing the user code. So at the end of the day, the microprocessor or a microcontroller has to execute the user code. There is no doubt about it. But before it executes the user code, it is necessary that the microcontroller has to undergo an initialization process, which is dictated by the manufacturer of the IC, and it comes to a known standard state. after which it is free to execute the user code, which means two things you have to be very clear with regard to reset circuit. 200% it is essential that any microcontroller or any processor for that matter has to undergo the reset cycle. If it doesn't undergo the reset cycle, it is most likely that the microcontroller or a microprocessor doesn't perform the way you expect that fellow to perform. That is guaranteed, which means I have to somehow make sure that the microprocessor or a microcontroller undergoes the reset cycle. That is point number one. Point number two, what exactly the microprocessor or a microcontroller do during the reset operation is something which is manufacturer defined. I don't have any role in that. So all I have to do as a designer is to make sure that the microcontroller undergoes the reset process. What exactly the microcontroller does during the reset operation is beyond my scope. I am not bothered about it because it is something which is dictated by the manufacturer. What exactly it does is the microcontroller initializes itself and it performs a lot of housekeeping functions, like it initializes the stack pointer, initializes the program counter, initializes all the serial ports and parallel ports, wipe the initial critical registries inside. So it performs a lot of housekeeping functions, and it will ensures that it is ready to execute the user code. So that is what it is as far as the reset is concerned. Any microcontroller or a microprocessor is always associated with the reset pin. For our microcontroller, it is pin number 9. So there are two types of resets. One is an active high reset. The other one is an active low reset. Active high reset and an active low reset. Active high reset means the microcontroller enters into reset mode. The microcontroller enters into reset mode if you make the reset pin to logic high. If you make the reset pin to logic high, the microcontroller enters into reset mode for active high resets. If you make the reset pin to logic 0, the microcontroller comes out of reset. For active low reset, it is exactly the opposite. The microcontroller enters into reset if the reset pin is equal to S0. If you ground the reset pin, the microcontroller enters into reset. And if you make the reset pin to logical 1, then the microcontroller comes out of reset. So that is the basic difference between an active high and an active low reset. Functionally, both of them are same. They are basically distinguished by the way you force a microcontroller into reset mode. For active high resets, we force the microcontroller into reset mode by connecting the reset pin to logic high. For active low reset microcontrollers, we force the microcontroller to reset by making that pin to logic 0. That is the difference. Now, for our microcontroller, how do we construct a reset circuit? So we have already discussed this in our original class. We construct our reset circuit by connecting a simple RC circuit. I have a capacitor and I have a resistor in series to it. This is a 10 microfarad polarized capacitor, plus and minus. This is 8.2K resistor. This is my power supply VCC. This is the output voltage that I connected to reset pin to reset, which means what? I connect this output pin, output of this fellow directly to the reset pin of my microcontroller. This is what I do. So if you draw the graph between, this is my time axis. So this voltage is essentially voltage across resistor VR. So if I'm going to draw a graph between VR versus time, initially at time t is equal to 0, once I power on this particular circuit, the capacitor's initial voltage is 0 volt. So according to Kirchhoff's voltage law, the power supply voltage VCC is equal to voltage across the capacitor plus voltage across the resistor. So initially VCC is plus 5 volt. So this is at plus 5 volt. Capacitor's voltage is at 0 volt. So naturally VR plus VC is equal to 5 volt. VC is 0 volt. So naturally VR has to be at 5 volt. So initially VR takes 5 volt. So it starts at plus 5 volt. And as time progresses, if the capacitor's voltage is 0 volt, I'll also draw the capacitor's voltage here. VC is initially at 0 volt. So as time progresses, this fellow slowly charges. So capacitor exponentially charges high. This is my capacitor voltage. At the same time, what will happen to the voltage across resistor? Voltage across resistor will exponentially drop down like this. This is my voltage across resistor. At any point in time, if you add these two voltage, you will always get 5 volt, plus 5 volt. Now the actual input that is actually going to the reset pin is the voltage across resistor, which is this part. So at time t is equal to 0, this pin is connected to plus 5 volt. As time progresses, the voltage across resistor drops below somewhere below 1.5 volts. So it drops down to logical 0. So at time t is equal to 0, it takes a logical 1. It remains at logical 1 as long as the voltage across resistor is able to maintain a voltage above 1.5 volt. And the moment it crosses that 1.5 volt, it goes to logical 0. So Boolean wise, if you see what is the voltage seen by pin number 9, from time t is equal to 0 to time t is equal to delta t. Delta t is this time where it crosses this 1.5 volt. So at that time instant, this pin is remaining at 5 volt or Boolean 1. The moment it crosses this 1.5 volt threshold, it goes to Boolean 0. So which means during this delta t period of time, the microcontroller remains in reset. Once it falls below this one, the microcontroller comes out of reset. And this is the reset pin of our microcontroller, which is an active high reset, by the way. Active high reset means it remains at reset during Boolean 1, and once the input voltage takes a Boolean 0, it comes out of reset. So this is how we construct a reset circuit for a active high reset. For active low, you have to simply swap these two fellows. This is the simple circuit, reset circuit that we have already discussed. For active high reset, this is the voltage that is actually going to the reset pin, which is VR. This is my VC. The summation of the two should be my power supply voltage. So the actual voltage that is going to the reset pin is this voltage. So once it crosses this threshold, it comes out of reset. So if you are drawing a graph in Boolean sense, pin number 9 or reset pin takes a Boolean 1 or logic 1 till this time period. After this time period, it takes a logical 0. So which means during this time period, it remains in reset. And after this period, it executes the user code. So that is the logic behind it. And it is also possible for you to connect a reset switch. Reset switch is connected exactly across the capacitor, which means when you press this reset button, what will happen? When you press this reset button, this capacitor is short circuited. The positive and the negative terminal of the capacitor is short circuited. So when the capacitor is short circuited, what will happen? The capacitor will discharge all the charge possessed by it, so and it will become 0 volts. And the reset pin is short circuited to the power supply pin. So whenever you are pressing the reset switch, if reset switch is pressed, these are the two things that will happen. What is the first thing? First thing is reset pin is connected to plus 5 volt. How it is connected to plus 5 volt? It is connected to plus 5 volt via this path, via this switch. So once it is connected to plus 5 volt, the microcontroller get into reset mode. That is why this pin is called, this switch is called reset switch. So whenever you press this switch, the microcontroller automatically enters into reset mode. Second one, the capacitor discharge all the charge. Which means this time t is equal to 0 condition will happen. This condition will happen whenever you are pressing this button. So that particular reset switch we will add whenever you wanted to reset the microcontroller in the middle of the operation. The third important component is the oscillator circuit. The oscillator circuit is called the heartbeat of the system. It is called the heartbeat of the system because this is the one which supplies the continuous clock pulses for the operation of the microcontroller. If the heartbeat of the microcontroller stops, the microcontroller stops its operation. Which means this is the most important part of your microcontroller activation circuit. Fortunately, the oscillator is built inside. If you look into this block diagram, the oscillator is built inside. All you have to do is to connect the crystal across pin number 18 and pin number 19 respectively. Pin number 18 and 19 is the crystal pins where you connect the crystal across 18 and 19 with the two stabilizing capacitors. This built-in oscillator supplies continuous clock pulses. This chain of clock pulses is what is used by the microcontroller for synchronizing all the internal operations. As a designer, you have nothing to do with regard to design of the oscillator circuit because that is something which is already available inside. As a designer, your job is to decide what is the frequency of this fellow, what is the frequency of the crystal that I connect. Because it is the frequency of this crystal oscillator which makes all the difference. As I have already told you, suppose let us say I connect frequency f is equal to 12 megahertz. This oscillator is connected to 12 megahertz. For the same microcontroller, without changing the microcontroller, I swap this particular crystal with a separate another crystal with 24 megahertz. By only changing the crystal frequency without changing the microcontroller from 12 megahertz to 24 megahertz, what am I essentially doing or achieving is I'm increasing the performance of my microcontroller twice. So the larger the crystal frequency, the better the performance of the microcontroller, which means increasing the crystal frequency is a crooked way of increasing the performance of the processor. Are you able to understand? If you are able to increase the crystal frequency, the microcontroller is able to perform at a faster rate. But it doesn't mean that you can keep on increase this crystal frequency as you like. As I told you, any microcontroller has specific limits, lower limit and a upper limit. You can connect any crystal between these two limits. Just like I always give engine speedometer example for this. If you take an engine speedometer, you have 0 kilometers per hour to say 160 kilometers per hour. So the engine can support any speed limits between these two limits, lower limit, upper limit. Just like that, any crystal, any microcontroller has two limits, 0 megahertz to 24 megahertz, for example, for 8051 core. For a different processor, it will have a different higher upper limit. Between these two limits, you can connect any crystal frequency. As I already told you, connecting a crystal frequency has to come with a small amount of common sense, because you cannot keep on connect higher crystal frequencies just because you want the microcontroller to operate at a higher speed. The reason being, if you are going to draw a graph between power consumed by the microcontroller on the y-axis and the frequency of operation on the x-axis, it goes in a perfect linear straight line. What does it mean? It means for a low frequency microcontroller, it takes small amount of power, T1. If you double the frequency, it takes 2 times the power as the old power. So the microcontrollers increasing this crystal frequency has a deep impact on power consumption of the processor. The other impact that the microcontroller's power, the oscillator frequency has is for the electromagnetic interference noise, EMI noise pickups. If you draw the graph between frequency versus EMI noise, again it has a perfect straight line, which means at higher frequencies, the possibility of noise pickups by the system is also much higher. So the moral of the story is, just because my microcontroller supports up to 24 megahertz or 40 megahertz or 100 megahertz, you will not connect that particular microcontroller with a higher frequency just because you want the microcontroller to operate at a higher frequency. You would connect a microcontroller somewhere in the middle for its safety. That is the moral of the story. So the exact crystal frequency that we will be using in all our practical applications is 11.0592 megahertz. This has something to do with whether the microcontroller is using serial communications or not. But even otherwise, I don't recommend you to use a higher frequency just because I want my microcontroller to operate at a higher performance. You just fix a speed somewhere between the lower and the upper limits. So that is something that I have to tell you regarding the oscillator frequency. And last but not the least comes the firmware locator. The firmware is nothing but the microcontroller code that I developed for the microcontroller, which I have to put it inside. But 8051 microcontroller has the provision for taking the source code from the external memory. You can also connect an external ROM and connect the source code externally. So 8051 microcontroller has the option for fetching the source code either from internal ROM or from external ROM. So if there is a situation like this, you have to explicitly tell the microcontroller from where exactly it has to fetch the source code from, whether it has to fetch the source code from internal ROM or external ROM. In 99.99% of the cases, we will make the microcontroller to fetch the source code from internal ROM. So this particular pin, the external access pin, pin number 30. Pin number 30 is called external access. If you see, there is a bar on top of this, EA bar. If EA bar is true, when do I make it true? I make it true by connecting this pin to ground pin. Because this is an active low line, if I connect this line to ground, EA bar becomes true. So external access becomes true. External access becomes true. External access becomes true means what? The microcontroller will fetch the source code from external ROM. External ROM. But that is not how I want it. I want my microcontroller to fetch the source code from internal ROM, not from external ROM. In that case, I have to make this fellow false. How do I make that fellow to false? This external access I connect it to power supply pin, VCC. If I connect this external VCC, external access becomes false. If external access becomes false, it means it is internal access. In that case, I put my source code internal to the microcontroller. The microcontroller takes the source code from internal memory. So firmware locator is a way of telling the microcontroller from where it has to fetch the source code from. Whether it has to fetch the source code from external memory or whether it has to fetch the source code from internal memory. I don't want the source code to be fetched from external memory. So I don't want it to be used this way. I want it to be used this way. So I deactivate my external access and I make it false by connecting this pin to power supply pin. So that is what I do. Pin number 31 is external access pin, EA pin. So if EA pin is equal to 1, which means the firmware is onboard ROM. Onboard ROM means it is not onboard, it is actually on chip. On chip means it is present inside the microcontroller. If EA is equal to 0, which means if you make external access true, then firmware is from external ROM. In that case, external ROM supplies the source code. So we want to be used by this way, which means I want the on-chip ROM to be used, not the external ROM. So let us consolidate steps 1 to 4. What are the, before I move on, I just once again wanted to get your inputs. Are you, all of you are with me? Or are you able to follow what is going on here? Okay. Now let us consolidate our talking points here. First requirement is my power requirement, which means I connect power supply, this pin to power supply. I connect that one to power supply, and 20th pin has to be connected to ground. That is my ground pin. So that is my first thing. Second one is my reset pin. So reset is constructed by using a RC circuit. So one end of this RC circuit goes to power supply. Voltage across resistor is connected to the reset pin. This is 10 microfarad. This is 8.2K. The third one is my crystal pin. Crystal is connected at pin number 18 and 19. So I connect the crystal this is crystal 2, this is crystal 1. I have two capacitors. Both of them are connected to ground pin. This is 33 picofarad. And the frequency of operation of this is 11.0592 megahertz. The fourth one is external access pin. I connect this pin also to ground, to power supply. External access is equal to logical 1, means external access equal to false. In that case, we take internal room. So these are the 4 steps. Step 1 is power. Step 2 is reset. Step 3 is oscillator. Step 4 is firmware locator. And the 5th step, step 5, is the firmware locator part. Firmware locator is the last step where we need intelligence to be put inside the microcontroller by virtue of writing a small piece of code. We write a source code either in assembly or in embedded C, converted that into a binary file. In this case is called a .hex file, and we put that hex file into the microcontroller so that the microcontroller executes the source code that we wanted to run, which is the last step. So steps 1 to 4 refers to the logical steps, electrical requirements. 1 to 4 is my electrical requirement. 5th step is my logical requirement. And all the 5 steps have to be satisfied for the microcontroller to work. If any one of the 5 is not satisfied, which means if you satisfy first 4 electrically, and if you don't write a source code, the microcontroller will not work. On the other hand, if you write all the program perfectly, and if the electrical requirements are not satisfied, still the microcontroller won't work. The microcontroller will work if you satisfy all the electrical requirements, as well as if you write a proper program, then the microcontroller will work. Okay, so I stop today's introductory class because I don't wanted to, I just wanted to revise something today instead of taking you to a class which you are not aware of, because this is the first time that we are meeting in the online session. So I just wanted to revise something that we have already done instead of taking a new class, because if there are some fine tuning required for the online delivery, we can do that today and apply that tomorrow and take it at a fresh level. So that's what I wanted to share you today. So I now open the floor to the people to ask questions if you have any. So what I do, if you have any doubt, you please raise your hand. I'll unmute you and answer your question. If you have, or the other way of taking that is, if you can put your query in the chat window, I'll answer them one by one. So you can just, if you have any doubt, you just type the query or doubt in the chat window so that I'll address them to all of you. Because if I unmute all of you, it will become a total confusion here. I'll share you this PPT to your WhatsApp group. You can have a look of it for your reference. If you have any doubt, you can just share it in the group. Resistor 8.2K, why? Resistor 8.2K is not decided by us. It is given in the manufacturer's data sheet. The resistor and the capacitor's time constant should be good enough to complete the reset operation. One of you have asked a question. I think it is Sivasankar. Sivasankar has asked a question, why are you putting 8.2K in the reset circuit? Okay, so let me give you a brief idea about it. The reason why we are giving 8.2K is because this. See, when you are designing a RC circuit like this is a capacitor, this is a resistor. This is my VR, this is my VC. Now, when you are going to draw a graph between VR versus time, which is this voltage. So time t is equal to 0, it starts at 5 volt. So it operates at plus 5 volt. And as time progresses, it drops down. And it drops down to 0 volt or near 0 volt, typically at 5 time constants. One time constant t here is the product of R and C in a RC circuit. So if the time constant is larger, if t is higher, it will take more time for the circuit to reach that 0 volt. If I still increase the time constant, it will take more time to take that 0 volt. So how am I going to increase the value of time constant? You can increase the value of time constant by increasing the product of R and C. So if you keep C as constant, if you increase the value of R, then the time constant value will increase. So instead of putting 8.2K, if I put 82K, for example, the time constant value will increase by 10 times. So what will happen? Originally, if the voltage across resistor has dropped to 0 volt or near 0 volt at some time, it will take 10 times more time for the circuit to reach that value of 0 volt here. So essentially, what am I doing? By increasing this time constant t, I am increasing the value of the duration for which the circuit remains in reset. So if you want to understand it more clearly, I will draw another graph and show you, so that it will become much clearer for you. So this is one graph. This is time t. This is voltage across resistor. So initially it stops at 5 volt, and then it takes 0 volt here, let us say. This is when R is equal to 8.2K. Now if I put the same R as 82K, 10 times much higher value, the resistor will take 10 times longer time to reach that value of 0 volt. Oops. So it will take 10 times longer time to reach that 0 volt, like this. Now what is the difference it makes? Now the time duration at which it crosses around 1.5 volt is here, which means the duration for which the circuit remains in reset is this delta t. The circuit remains in reset for this much amount of time here. Whereas here, the duration for which the circuit remains in reset is pretty high. This is the reset period. I am just giving it in a very short here, but it is actually much higher, at least 8 to 10 times higher. So effectively, by increasing the value of R, what are you doing? I am increasing the value of time constant. If I increase the value of time constant, what will happen? The time for which the microcontroller remains in reset is much higher. So you can control this delta t, the duration for which the circuit remains in reset, by controlling the value of R. So it is a design parameter that you can play with. You can actually calculate what exact time period that you want, because if you know the value of what is the expression for the voltage across resistor, is equal to VCC into e power minus t by t. So if you know the value of RC, you can figure out what is the value of R and C that is necessary for you to control this delta t. But it is given in the data sheet that if you are giving 8.2K or 8200 ohms, it is sufficiently large enough for the microcontroller to complete the reset operation. So that is something that is given in the data sheet, that is not decided by us. but anywhere between 8 to 10K is good enough. So you need not even have to very strictly limit to 8.2K. Okay, so any other doubt? Balamurugan has asked another doubt. Can I use external access 31 as an extra code, like I will have a code 1 in internal ROM, and under condition controller will take code from EA. Then I'll have two codes ready to run according to the conditions given. Yeah, that is possible. You can play with the external access. What is he asking is whether it is possible to programmatically control external access so that the microcontroller can fetch the source code both from input as well as from output. Yes, it is possible. It is possible that you can play with external access so that it can take the source code both from internal as well as from external. It is again possible. Any other doubts you have? If you have any doubts, you please share it across here. So I am taking your attendance from the participation list here. So I'll give you the attendance based on what is Balamurugan asking again. Only two or more. Only two means you can only have two choice, either internal or external. Internal is the memory which is present inside the microcontroller. External means the memory connected outside the microcontroller. Outside the microcontroller, the memory size is limited by the number of address pins. In this case, it is 16 pins, which means you can connect a maximum of 64K. It is possible to extend this beyond that, but straightforward way, it is 64K. So these are the only two choices available. You can, ping me directly to my personal number, or you can put your questions to this mail ID, sundar@tech.edu, or you can ping to my mobile number. Okay, thank you all joining today. We'll meet the same time tomorrow. Tomorrow we'll discuss LCD interfacing. See you all. Bye. Don't go outside your home. Whatever you wanted to do inside your home, because we are having a very serious threat of corona elsewhere. So don't go to malls or beaches or playgrounds and create trouble for yourself. Act smart and sit and do something at home. Don't